Hey, it's Jim, and this is level 1 of the CFA program, the topic on fixed income, and the learning module on yield-based bond convexity and portfolio properties. I'm hoping you recall that we've had some really good conversations on interest rate risk over the last couple of learning modules. I'm also hoping that you'll recall that I have said to you that duration is a great measure of interest rate risk, but that it needs to be coupled with this concept of convexity. I also told you that convexity was a conversation we were going to have at some other date. Well, today is that some other date. This is what I'll be emphasizing in this learning module and also the next one, that to measure interest rate risk, you need to understand both duration and convexity. Now, having said that, I will agree that interest rate risk can be captured mostly by its duration effects. But there are times when a convexity adjustment is going to be super important. Sometimes the convexity adjustment is close to zero. Sometimes it's this big. And we'll talk about that as we go through this learning module. Now, the good news for you guys is that every one of these action words asks us to calculate. There's also a couple of interprets and explains in there. But at the end of this learning module, there are 9 questions that I want you to go to and solve. And I think you need your calculator for about 8 of them. So those of you who love math, this is going to be a really, really fun recording. So let's go ahead and remind ourselves that what we're trying to do here is we're trying to evaluate a bond or a bond portfolio. What do we know? That basically there are 2 types of risk when you invest in bonds. There's default risk, which we're not talking about at all here today. We had a completely separate learning module on default risk. We're talking about interest rate risk here. What does that mean? That means that if interest rates increase, let me say this a couple of different ways, if yields increase, if the yield curve shifts upward in a parallel manner, then this is bad news for our bond or our bond portfolio. Bond prices fall, right? So the question then becomes, how do we measure the degree or the magnitude of that bond price decline when yields rise? Or alternatively, how do we measure that magnitude of the bond price increase when yields fall? We need both duration and convexity. So look down at the second gray box there. You should know this from our previous discussions. Duration is a first derivative, and it's a linear approximation of the bond price change. What we need to do is make a convexity adjustment to reflect the non-linearity of the relationship between yields and prices. So we're going to do the same thing we did in the previous learning modules. We're going to have this duration effect, but then we're going to add a convexity. And you'll see this here in this picture. All right, so there's the yield on the horizontal axis and price on the vertical axis. Notice that there's a straight line going from one intercept to the other. Well, that's the duration. Duration is a linear relationship. But we know that the relationship between yields, which is an interest rate, right, and price, which is dollars, that relationship is not linear. In fact, it's convex. So you can see that little curvy line there. That reflects the true relationship between yield and price. So as you can see, duration only captures a large component of it, and then that vertical red line here up there at the top left and the vertical red line down there at the bottom right, that reflects the convexity adjustment. So I want to come back to that illustration, but look down at the bottom equation. In blue, we have this modified duration effect. We did that in those previous 2 learning modules. But then what we're going to do is we're going to add, and that's a plus sign there, we're going to add convexity and yield. Now, convexity is a second derivative, so it's not surprising that we're going to have a 1/2 in there. It's not surprising that we're going to have something that is squared. I'm guessing that you don't really need to worry about how we actually take second derivatives, but that's called a convexity adjustment. And so we're going to add, right? So that's a plus sign. I've said that before. I'm going to say it again. So notice when yields fall, This is good news for a bond, but duration doesn't capture all of the good news. But when yields rise, this is bad news for investors, but duration doesn't capture some of the good news in the bad news falling. Did I say that correctly? I think I did. But go back up to the gray box at the top. This is exactly what I was saying. Can I read this to you? When the yields fall, the price increase is underestimated with solely considering duration. When yields rise, the price decrease is overestimated. All right, so there we go. This is exactly what I was saying, and this is why we have the plus sign there. Now recall that we had a formula for approximate duration. Now at the bottom here, we have a formula for approximate convexity. And it looks an awful lot like our duration, but we have to add a couple of other things because convexity is that second duration. So take a look at that equation at the bottom. You probably have to memorize it. We'll do a couple of examples here as we go through the slide deck. So here's a part of that LOS where we need to interpret, and I think we've done a really good job of putting those colored boxes there. Factors impacting convexity. Notice that after the equal sign, we have higher convexity under each of those. So just remember the 4 L's: longer maturity, lower coupon rate, lower yield to maturity, larger disbursement of cash flows. If you remember those 4 L's and equate those to higher degrees of convexity, then I think you'll be able to answer any of those interpret questions about convexity and its relationship to some of those bond input variables. Now look down at the bottom here. This is really important. Bonds with high convexity are less risky. So let me go back to this illustration here. Let's partition this graph into its two components. So let's go right in the middle and let's assume that yields fall. So what happens? When yields fall, that's good news for the price of the bond. But according to duration, the bond price goes up by just this much, right? Whatever that amount is. But convexity drives the bond price up this much, right? So convexity is good news when the yields on the bonds fall. Now let's go in the other direction. Let's suppose that yields rise. Well, that's bad news for the price of the bond. But what convexity does is it raises the price above that which is predicted by duration. So when yields rise, this is bad news for the bond, but convexity makes it less bad news. Does that make sense? Less bad news. I think that makes sense. So my point is, let's go back here to this slide. The orange teardrop point. Bonds with high convexity are less risky. In fact, bonds with any level of convexity. I mean, let's go back here. Look, you could draw that curve, almost on top of the duration line. And even with just a little bit of convexity, it tells you that bonds are less risky. Which means, and this is exactly what I was saying, they perform well in varied yield scenarios, and that last teardrop point is exactly what I was trying to say when we went this way and we went that way. So I think that's that last teardrop point, that's a really good thing to memorize. So let's get back to the calculations. All right, we have a bond here, 3 years to maturity, 2% coupon, that's annual, by the way, 2% yield to maturity. So, of course, that bond is priced at its par value. Let's go ahead and find the modified duration, and let's find the convexity, and then let's use those estimates to determine what happens if there is some kind of a yield change. So what we've done on this next slide is replicate the table. So I want you to look at the table. Let's compute that duration. And you guys should be familiar with this from before. Notice that the duration is 2.94. How did we get that? Well, all we did was we multiplied the time to receipt column by the weight column, right? So 0196, that's just 1 times 0196, right? That makes perfect sense. So the 0384, what is that? That's 2 times the 01922, and then 3 times the 96118. So we did that in the previous learning module. So you should have no problem computing that duration of 2.94 years. Makes perfect sense, right? So how about, now look at the LOS, calculate convexity. So we need to go to this far right column, and there are the answers, 377, 1108, and then 11.087. So the convexity of this bond is 11.235. Now, if you go to the actual reading, what the Institute does is it tells you how to calculate these in general, gives you a formula, but it doesn't really go through each one of these. So this is what we've done for you down here at the bottom. Now, there's no shortcut, so you're going to have to memorize this here. So there's convexity in year 1, 2, and 3. And here is the simplest version of the equation that we could come up with. All right, so what we're going to do is take that time to receipt column. So there's 1, 2, 3. So look inside of the brackets. There's 1, 2, 3. What we're going to do is we're going to multiply that by column 1, 1, 2, 3, plus 1. So that plus 1 is standard, right? So look at that inside of the parentheses, we're going to have 1 times 2, then 2 times 3, then 3 times 4. And then if we had a year 4, we'd have 4 times 5. If the Institute asked you to calculate the convexity of a 49-year bond, I would pick B and move on with my life. But I don't want you to get too upset about this, because you can calculate that 11.235 on the exam if you're called to do that. So remember, all we're doing in this first part is we're going to say 1, 2, 3 times 1 plus 1, 2, 3. All right, that's the first part. And then all we're going to do is multiply it by the column of weights, which we did for duration. So, right, we're piggybacking on our duration conversation. So there's the 196 and the 1922 and the 96118. And then all we're going to do is divide that thing by 1 plus the yield, right? Let me go back here just to confirm that for everybody. Yield to maturity, 2%. 1 plus the yield to maturity squared. So there you go. There you get the 377, the 1108, and the 11087. If you sum those, you get convexity of 11.235. So go ahead and take a deep breath and say to yourself, you know what, Jim, maybe I can do this, maybe I can't. I promise you that you can. Now, here's the thing. The Institute may give you just what we did here. 3 years, 2%, 2%, and say go ahead and compute the convexity, in which case you're going to have to replicate this equation. Replicate these equations inside of that table. All right. So Macaulay duration we did of 294. There's our convexity. Then we can divide that Macaulay by 1 plus the yield to get the modified duration. Remember the difference between Macaulay duration. We did this before, but I'm happy to repeat it. Macaulay duration is really just a weighted average time to maturity. Remember what I said in that last recording, modified duration is kind of like a present value of the Macaulay duration. And that modified duration is really, really important because it's going to allow us to estimate the percentage change in the value of our bonds. All right, you ready for this? So what was that equation right there? Well, skip down to the bottom. So there's approximate convexity. Here, I was gonna go back to here at the bottom, but I didn't need to because it's right there. So what are we going to do? We need the price of the bond if the yield falls, and the price of the bond if the yield rises. We need its current price and the yield change. So back here, what did we say? Find the approximate modified duration and approximate convexity with a 10 basis point yield change. So what we're going to do is we're going to go ahead and simply say, well, there's our price. Look at the 3 bullet points. So there's our price. We knew it was priced at par value. So if the yield goes from 2% down to 1.9%, then the price is 100.288 and all those digits. If the yield goes from 2% up to 2.1%, then the price is 99.71 with all of those digits. Now, you might be asking yourself the question, do I really need to go out, excuse me, to 100 significant digits? And my answer as an academic is no, you don't really need to do that. However, the Institute inside of the reading, they go out fairly far. I don't really know what the definition of fairly far is, but you guys will have to figure that out on the exam. But I don't think it's really that big of a deal if you cut it off at 3. I always tell my students, if you go out to 3 decimals, you ought to be somewhere in the ballpark. Nevertheless, what we can do is compute that approximate duration using what we just calculated in those time value of money simple bond pricing model equations, and you get all that stuff and you get 11.2349, which now wait a minute, let's go back here, we computed at the table as 11.235. So here's my advice on the exam. I'm guessing that sometimes the Institute might give you the problem just like this, 2%, 2%, and ask you to put together this table. And sometimes the Institute might say, hey, here's the current price of 100, here's two possible future prices, 100.28, 99.71, in which case then you can use this equation. So once again, just like I said back in the duration conversation, you can either use the table or the equation. You can do the same thing here for convexity, and it depends really on what the Institute provides you in the question stem, which will determine which one of those 2 methods that you're going to have to use. So my advice is just to know them both and then move on with your life, right? The more you know, the better off you are for the exam. That's like Newman from Seinfeld says, when you control the mail, you control information. And so what I'm saying to you is when you control all of the ways to solve these problems, then you have a better chance of success. Now, look, I really don't want to inundate you to memorize tons and tons of these formulas. I'm just trying to prepare you so that you don't get these questions wrong on the exam. Because, look, you ought to be able to come up with 11.23, right? Let's go ahead and look at another example. In this case, we'll look at a 2-year bond, 4% semi-annual coupon, and this bond is priced at par. Now make certain that you're sensitive. In our previous example, we had an annual pay bond. Here we have a semi-annual pay bond, so we're going to have to make a slight adjustment or two as we go through the next couple of slides. But the purpose of this next section is to address the LOS, which asks us to calculate the percentage price in the change of a bond for a specific change in yield. And what's going to result is that when we use duration and convexity, hopefully we'll come out with a more accurate estimate of that price change. So that's an important concept. That's the motivation for what we're doing here in these next couple of slides. Let's start with that first orange point. All we're doing there is computing and verifying that the bond is priced at its par value of 100. Then what we're going to do is we're going to say, let's suppose that we have a 1% decrease in yield, and that's from 4% down to 3%. So we can just do the math there, and you get 101.927. I mean, you can do it the long way, like we did in this slide, or you can get out your financial calculator and do it using those 5 time value of money buttons. If the yield increases to 5%, then the price of the bond is going to fall. You get 98.11 down there. And then somewhere in the middle there, under each of those prices, we have calculated the percentage change in the price of the bond. That's just an F over P minus 1. So we put in purple, if the yield falls to 3%, the bond increases in value by 192.72. If the yield increases to 5%, the bond value loses 1.8810%. All right, so those are calculations that we made using our bond pricing model. So the question then becomes, what happens if we use duration and convexity? What numbers will we get? Will we get the purple number? Will we get the green number? Or will we get some other number? All right, so here's another table. I'm going to go ahead and let you guys pause the recording right now. and compute the Macaulay duration, 3.88. Compute the convexity, 18.48. Go ahead and compute it like we did back in here. I'll take you back. I want to go all the way back here. Here you're going to use those convexity formulas and the duration formulas, right? I'll let you guys pause and do that. Come back and I'll pick up here at the bottom with those bullet points. So we need to divide by 2 to get the annualized Macaulay duration. We need to divide by 2 squared to get the annualized convexity. So 194, 4.620. Then we can, of course, take the present value. Remember I said this before. The present value of the Macaulay duration, that gives us modified duration. Now that modified duration there, what does that tell us? Let's go back to what we learned in the previous recording. We know that that modified duration is going to give us the percentage change in the price of the bond. We're just calling that the duration adjustment, right? So look down at that last point. The convention is to just say, okay, 100 basis points change in the yield will result in a plus or minus, right? There's a plus or minus sign of 1.9039%. So that's where we get the modified duration, 1903. That translates into a percent change in the price of the bond. All right, so that's just duration. What we need to do is we need to add the convexity adjustment. So our change in yield is a 0.01, but one of those is positive and one of those is negative. So if you do the math, there's the red over on the far right. If you do the math, you're going to get 2 different answers because of the non-linearity in the relationship. Let me go back here. There in blue, that's the linearity of the relationship, right? So we add the convexity adjustment, and then we get the 1.972 and the 1.8808. So what we've done in this results summary table is show you how much more accurate using duration and convexity. So what I want you to do here just quickly is compare column 2 and column 3, right? So there's the actual blue and green that we computed a few moments ago. Compare that to the blue. And the difference is, what is that? 0.0233%, 0.0229%. But if we use duration and convexity, notice how much more accurate we are. So that's beautiful. The difference is 0.0002%. So it's 0.00, there's a whole bunch of zeros in there. So this is a great illustration of, and let me just go back here. Where did we have this at the top, right? Use both duration and convexity for a more accurate bond price change estimation. So voila, as my mother used to say to me when I was a little dude. I didn't know what that meant then. I still don't know what it means now, but it might mean something like abracadabra. There's a great result. So look at the 2 arrow points at the bottom. Convexity adjustment enhances precision. So we always have to make this convexity adjustment. I'm hoping that you're thinking along the following lines. Are you saying to yourself, hey, Jim, I'm so glad that you warned us in those previous 2 recordings that what we're doing in duration is really important, but convexity is going to be an extra added value to our understanding of interest rate risk. Let me repeat this. Duration captures most of interest rate risk. Convexity captures whatever duration doesn't capture to give us the full sense of interest rate risk. Let's go ahead and address this last LOS, calculate portfolio duration and convexity. This is super easy. This is just going to be a weighted average. So I'm not even sure I need to take you through the math, but of course I will. But then we'll talk about some limitations here. So what are we doing here? Duration and convexity measure interest rate risk. Oh my gosh, I've been saying that 1,000 times, right? So how do we do this if we have a portfolio of bonds? I mean, imagine having 10 bonds and they have their own each duration. and their own convexity. So what we're going to have to do is we're going to have to take a weighted average. You can do this weighted average of the cash flows or the weighted average of the individual bond metrics. So let's take a look at an example down here at the bottom. An institution invests in two bonds. One's a zero coupon bond, one's a semi-annual coupon bond. Let's go ahead and calculate the duration, convexity, and the estimated price change for that 100 basis point yield change. All right, so here we go. Let's look at the table. Zero coupon bond, 4 years to maturity, has a 0% coupon rate. That makes sense. It has a discounted price. That makes sense. 87. Yield is 3.5%. And the duration is 3.8647. You know, we might have had two columns for duration. If we had Macaulay duration there, you'd say 4, right? Macaulay duration is equal to the time to maturity on the zero coupon bond. But the modified duration, so that duration we have 3.8647, that's the modified duration, which is what we're going to use to estimate the price change. That should make perfect sense. There's convexity of 932. There's a semi-annual bond, 5 years, 4.5%. Its yield to maturity is 4.25. So this bond is going to sell at a premium. There's the duration of 444 and the convexity of 23. All right, so let's go ahead and see exactly what we're doing here. We're going to buy 500,000 of these bonds. So the zero coupon bond at $871. Now this is, of course, market value of $1,000. So we've got $435 million invested in the zero. We've got $505 million invested in the semi-annual coupon bond. So let's go ahead and compute the weights for each one. So if you sum 435 and 505, you get 941. So the weights there, you know, about 46% and 53 or 54%. So how do we calculate the modified duration of the portfolio? Well, what did I say just a few moments ago? It's just going to be a weighted average. So take the 463 times the modified duration of 386, and then the 537 times the modified duration of 444. You get 4.175. We're going to go ahead and do the same thing here on the far right-hand box for the weighted average convexity. 463 times the 19 and 537 times the 23. And we're going to go ahead and get that 21.36. So what we can do, and we're going to let you guys do this here, notice that estimated price change is 4.0677. What I want you to do is go ahead and use that equation right there in the first embedded bullet point, and I bet you can come up with that 4.0677%. Let me address that last part of the LOS, the limitations of these measures. I don't think I've said this so far in this recording, but I know I said it in one of the previous two recordings, is that the duration effect and the convexity adjustment, these work super, super well if we have, are you ready for this? A parallel shift in the yield curve. Either shift upwards or shift downwards. So the limitation of these measures is that the less of a parallel shift, the less accurate are these estimates. And that should make perfect sense. Now that leads us into a handful of the future learning modules in which we'll have a conversation about key rate duration, which is going to allow us to consider non-parallel shifts in the yield curve. So look for in the question stem where the institute will say something like, hey, suppose there's a parallel shift, or however they can describe it. That'll be your indication that you can get really, really accurate estimates using all the stuff that we've talked about over these handful of learning modules. So there are the 3 LOSs. I think we did all of those. I want you to go to the learning module right now. There are 9 questions back there. I think 8 of them asked you to calculate. So this might take you 20 minutes or so. I want you to work through those. I promise you can do all this, whether you have to compute convexity the long way or the kind of less than long way. I mean, there's really no shortcut in computing convexity. So, hey, I have tons of fun talking about interest rate risk. Thanks for watching, and good luck studying.